In mathematics and computer science, an algorithm is a self-contained step-by-step set of operations to be performed. Algorithms exist that perform calculation, data processing, and automated reasoning. An algorithm is an effective method that can be expressed within a finite amount of space and time and in a well-defined formal language for calculating a function. Starting from an initial state and initial input, the instructions describe a computation that, when executed, proceeds through a finite number of well-defined successive states, eventually producing output and terminating at a final ending state. The transition from one state to the next is not necessarily deterministic. Some algorithms, known as randomized algorithms, incorporate random input. The concept of algorithm has existed for centuries. However, a partial formalization of what would become the modern algorithm began with attempts to solve the Entscheidungs problem posed by David Hilbert in 1928. Subsequent formalizations were framed as attempts to define effective calculability or effective method. Those formalizations included the Gödel-Herbrand-Kleene recursive functions of 1930, 1934 and 1935, Alonzo Church's lambda calculus of 1936, Emil Post's Formulation 1 of 1936, and Alan Turing's Turing machines of 1936-7 and 1939. Giving a formal definition of algorithms, corresponding to the intuitive notion, remains a challenging problem. Informal definition. An informal definition could be a set of rules that precisely defines a sequence of operations, which would include all computer programs, including programs that do not perform numeric calculations. Generally, a program is only an algorithm if it stops eventually. A prototypical example of an algorithm is Euclid's algorithm to determine the maximum common divisor of two integers. An example is described by the flowchart above and as an example in a later section. Bulos and Jeffrey offer an informal meaning of the word in the following quotation. No human being can write fast enough, or long enough, or small enough to list all members of an innumerably infinite set by writing out their names, one after another, in some notation. But humans can do something equally useful. In the case of certain innumerably infinite sets, they can give explicit instructions for determining the nth member of the set, for arbitrary finite n. Such instructions are to be given quite explicitly, in a form in which they could be followed by a computing machine, or by a human who is capable of carrying out only very elementary operations on symbols. An innumerably infinite set is one whose elements can be put into one-to-one correspondence with the integers. Thus, Bulos and Jeffrey are saying that an algorithm implies instructions for a process that creates output integers from an arbitrary input integer, or integers that, in theory, can be arbitrarily large. Thus an algorithm can be an algebraic equation such as y equals m plus n, two arbitrary input variables, m and n, that produce an output y. But various authors' attempts to define the notion indicate that the word implies much more than this, something on the order of precise instructions for a fast, efficient, good process that specifies the moves of the computer to find, decode, and then process arbitrary input integers, symbols m and n, symbols plus and equals, and, effectively, produce, in a reasonable time, output integer y at a specified place and in a specified format. The concept of algorithm is also used to define the notion of decidability. That notion is central for explaining how formal systems come into being, starting from a small set of axioms and rules. In logic, the time that an algorithm requires to complete cannot be measured, as it is not apparently related with our customary physical dimension. From such uncertainties that characterize ongoing work, stems the unavailability of a definition of algorithm that suits both concrete and abstract usage of the term. Formalization. Algorithms are essential to the way computers process data. Many computer programs contain algorithms that detail the specific instructions a computer should perform to carry out a specified task, such as calculating employees' paychecks or printing students' report cards. Thus, an algorithm can be considered to be any sequence of operations that can be simulated by a Turing-complete system. Authors who assert this thesis include Minsky, Savage and Gurevich. Minsky. But we will also maintain, with Turing, that any procedure which could, naturally, be called effective, can in fact be realized by a machine. Although this may seem extreme, the arguments in its favor are hard to refute. Gurevich. Turing's informal argument in favor of his thesis justifies a stronger thesis. Every algorithm can be simulated by a Turing machine. According to Savage, 1987, an algorithm is a computational process defined by a Turing machine. Typically, when an algorithm is associated with processing information, data are read from an input source, written to an output device, and/or stored for further processing. Stored data are regarded as part of the internal state of the entity performing the algorithm. In practice, the state is stored in one or more data structures. For some such computational process, the algorithm must be rigorously defined, specified in the way it applies in all possible circumstances that could arise. That is, any conditional steps must be systematically dealt with, case by case. The criteria for each case must be clear. Because an algorithm is a precise list of precise steps, the order of computation is always critical to the functioning of the algorithm. Instructions are usually assumed to be listed explicitly, and are described as starting from the top and going down to the bottom, an idea that is described more formally by flow of control. So far, this discussion of the formalization of an algorithm has assumed the premises of imperative programming. This is the most common conception, and it attempts to describe a task in discrete, mechanical means. Unique to this conception of formalized algorithms is the assignment operation, setting the value of a variable. It derives from the intuition of memory, as a scratch pad. There is an example below of such an assignment. For some alternate conceptions of what constitutes an algorithm, see functional programming and logic programming. Expressing algorithms. Algorithms can be expressed in many kinds of notation, including natural languages, pseudocode, flowcharts, Dracon charts, programming languages or control tables. Natural language expressions of algorithms tend to be verbose and ambiguous, and are rarely used for complex or technical algorithms. Pseudocode, flowcharts, Dracon charts and control tables are structured ways to express algorithms that avoid many of the ambiguities common in natural language statements. Programming languages are primarily intended for expressing algorithms in a form that can be executed by a computer, but are often used as a way to define or document algorithms. There is a wide variety of representations possible, and one can express a given Turing machine program as a sequence of machine tables, as flowcharts and Dracon charts, or as a form of rudimentary machine code or assembly code called sets of quadruples. Representations of algorithms can be classed into three accepted levels of Turing machine description. 1. High-level description, prose to describe an algorithm, ignoring the implementation details. At this level, we do not need to mention how the machine manages its tape or head. 2. Implementation description, prose used to define the way the Turing machine uses its head and the way that it stores data on its tape. At this level we do not give details of states or transition function. 3. Formal description, most detailed, lowest level, gives the Turing machine's state table. For an example of the simple algorithm, add m plus n, described in all three levels, see algorithm #examples. Implementation. Most algorithms are intended to be implemented as computer programs. However, algorithms are also implemented by other means, such as in a biological neural network, in an electrical circuit, or in a mechanical device. Computer algorithms. In computer systems, an algorithm is basically an instance of logic written in software by software developers to be effective for the intended target computer to produce output from given input. An optimal algorithm, even running in old hardware, would produce faster results than a non-optimal algorithm for the same purpose, running in more efficient hardware. That is why the algorithms, like computer hardware, are considered technology. Elegant programs, good programs. The notion of simplicity and elegance appears informally in Nath and precisely in Chaitan. Nath. We want good algorithms in some loosely defined aesthetic sense. One criterion is the length of time taken to perform the algorithm. Other criteria are adaptability of the algorithm to computers, its simplicity and elegance, etc. Chaitan. A program is elegant, by which I mean that it's the smallest possible program for producing the output that it does. Chaitan prefaces his definition with, I'll show you can't prove that a program is elegant. Such a proof would solve the halting problem. Algorithm versus function computable by an algorithm. For a given function, multiple algorithms may exist. This is true, even without expanding the available instruction set available to the programmer. Rogers observes that it is important to distinguish between the notion of algorithm, i.e., procedure, and the notion of function computable by algorithm, i.e., mapping yielded by procedure. The same function may have several different algorithms. Unfortunately, there may be a trade-off between goodness and elegance. An elegant program may take more steps to complete a computation than one less elegant. An example that uses Euclid's algorithm appears below. Computers, models of computation. A computer is a restricted type of machine, a discrete deterministic mechanical device that blindly follows its instructions. Melzig's and Lambert's primitive models reduce this notion to four elements: discrete, distinguishable locations, discrete, indistinguishable count as an agent, and a list of instructions that are effective relative to the capability of the agent. Minsky describes a more congenial variation of Lambert's abacus model in his very simple basis for computability. Minsky's machine proceeds sequentially through its 5 instructions unless either a conditional if-then goto or an unconditional goto changes. Program flow out of sequence. Besides halt, Minsky's machine includes 3 assignment operations: 0, successor, and decrement. Rarely must a programmer write code with such a limited instruction set. But Minsky shows that his machine is Turing-complete with only 4 general types of instructions: conditional goto, unconditional goto, assignment, replacement, substitution, and halt. Simulation of an algorithm. Computer language. Nath advises the reader that the best way to learn an algorithm is to try it. Immediately take pen and paper and work through an example. But what about a simulation or execution of the real thing? The programmer must translate the algorithm into a language that the simulator, computer can effectively execute. Stone gives an example of this. When computing the roots of a quadratic equation, the computer must know how to take a square root. If they don't, then for the algorithm to be effective, it must provide a set of rules for extracting a square root. This means that the programmer must know a language that is effective relative to the target computing agent. But what model should be used for the simulation? Vani M.D. Boas observes, even if we base complexity theory on abstract instead of concrete machines, arbitrariness of the choice of a model remains. It is at this point that the notion of simulation enters. When speed is being measured, the instruction set matters. For example, the subprogram in Euclid's algorithm to compute the remainder would execute much faster if the programmer had a modulus instruction available, rather than just subtraction. Structured programming, canonical structures. Per the Church-Turing thesis, any algorithm can be computed by a model known to be Turing complete. And per Minsky's demonstrations, Turing completeness requires only 4 instruction types: conditional goto, unconditional goto, assignment, halt. Kemeny and Kurtz observe that while undisciplined use of unconditional GOTOs and conditional if-then GOTOs can result in spaghetti code, a programmer can write structured programs using these instructions. On the other hand, it is also possible, and not too hard, to write badly structured programs in a structured language. Towsworthy augments the 3 Bohm-Jacopini canonical structures: sequence, if then else, and while do, with 2 more: do, while, and case. An additional benefit of a structured program is that it lends itself to proofs of correctness using mathematical induction. Canonical flowchart symbols. The graphical aid called a flowchart offers a way to describe and document an algorithm. Like program flow of a Minsky machine, a flowchart always starts at the top of a page and proceeds down. Its primary symbols are only 4. The directed arrow showing program flow, the rectangle, the diamond, and the dot. The Bohm-Jacopini canonical structures are made of these primitive shapes. Substructures can nest in rectangles, but only if a single exit occurs from the superstructure. The symbols and their use to build the canonical structures are shown in the diagram.